Okay, so what were we saying? The invisible circle of physics, it exists, but it only exists in your head. There's a lot of stuff that's real that you can't see. You can't see God easily, but God is real. Now the invisible circle of physics is a reality, but it's one that you don't see. You have to conceptualize. God's not like that. God is real whether you conceptualize him or not. Anyway, let's talk about these phase differences. So if this is the displacement of simple harmonic motion, and you want to think about the velocity, velocity is always out of phase. So when the displacement is zero, the velocity is maximum, and when the displacement is maximum, velocity is zero, and then it carries on like this, so that we end up with a line that is completely out of phase. And it's hard to draw these and always get it right. It's easy to muck them up, but we get something like this. So that would be the velocity, and this would be the displacement. Now, so fact 2 that you need to understand is velocity is always a quarter of a cycle out of phase, a quarter of a cycle out of phase from displacement. 90 degrees out of phase. 90 degrees, circle, invisible circle, don't forget the invisible circle. Fact 3, let's talk about acceleration. Now, back to this thing. Think about the acceleration. It's speeding up as it heads towards equilibrium. It's getting faster. As it heads away, it's getting slower. It's permanently accelerating. Where's it accelerating towards? It's accelerating towards the equilibrium position. It always wants to be at the equilibrium position. It wants to be at the equilibrium position. That's what simple harmonic motion is always about. In fact, it turns out acceleration is directly proportional to displacement. So if you're twice as far out, your acceleration is going to be twice as big. Acceleration will be maximum when displacement is maximum. But guess what? They're 180 degrees out of phase. Why do I say that? Because displacement is maximum, it's in that direction. What direction is the acceleration? It's trying to get back this way. So the acceleration is 180 degrees out of phase from the displacement. Now another way of thinking about that is there is always a force. It's called a restoring force, because it's always trying to get back to the way things were. So if you move it out this way, the force is trying to get it back. If you try and move it this way, the force is trying to get it back. It's always a restoring force. So if we drew acceleration, it would always be opposite to displacement. Down here like this. I should be using different colours. I'm going to get myself messed up here because I'm not using different colours. Anyway, so this one is our displacement. So it's going to go like this. It's out of phase. 180 degrees out of phase. Half a cycle out of phase. Now, we can get formulas for these two equations by, if you remember back to any calculus that you've ever studied, we have for displacement x equals a sine omega t. Now if you differentiate that with respect to time, you get v equals a omega, it's not a w, it's an omega, cosine omega t. I think it's called using the chain rule. You get that. You can also work this one out. V equals A, sorry, I need to check this one. V equals omega a squared minus x squared. We won't bother deriving it, just know that you might see it. Now, if you go back to this one and you differentiate that, because acceleration is rate of change of velocity with respect to time, you get acceleration equals, you differentiate that, you get negative a omega squared sine omega t. A equals negative a omega squared sine omega t. Now 10 points if you can see a similarity between this and this. There's a big similarity. This is the same equation as this, but it's got a negative sign and it's got omega squared in it. So you can simplify that down to acceleration equals negative omega squared x. So that is a very important equation. These are very important equations, and that is a very important equation, and that is an introduction to simple harmonic motion, and that is physics today.